Every day we use things that contain a class of compounds called hydrocarbons. Hydrocarbons are compounds that contain hydrogen and carbon. This lesson is about the versatile nature of carbon and the classification of hydrocarbons. At the end of this lesson, you will be able to explain the vital force theory and its criticism, explain the versatile nature of carbon, define catenation, explain the tetravalent nature of carbon, define and classify hydrocarbons, and explain the homologous series. In the earlier days, based on the source, the compounds of carbon were classified into organic and inorganic compounds. In those days, scientists believed that organic compounds could only be produced by living organisms. They believed that organic compounds were produced under the influence of a vital force and could not be synthesized in the laboratory. This belief was shattered when Friedrich Wöhler, a German chemist in the year 1828, prepared urea from ammonium cyanate, which is an inorganic compound, without the aid of any type of force such as vital force. Today, over 10 million organic compounds are known, and this number is constantly increasing. This number is far more than the total number of compounds of all other elements put together. The existence of such a large number of organic compounds is due to the unique properties of carbon. The unique properties of carbon are tetravalency, catenation, and formation of multiple bonds. Let's focus on the first unique property of carbon. In order to complete its octet, carbon shares 4 electrons with other atoms, forming 4 covalent bonds. This is known as tetravalency in carbon. The next property is catenation, which is the phenomenon of self-linkage among identical atoms to form a long chain of molecules. Carbon exhibits maximum catenation when compared to elements like sulfur and silicon due to strong carbon-carbon bonds and tetravalency. Due to this catenation, carbon atoms can form various types of straight chains, branched chains, and ring structures, thus giving rise to a large number of compounds. For example, N-butane is a straight chain compound, 2-methylbutane is a branched chain compound, and cyclobutane is a cyclic compound. The last unique property is the formation of multiple bonds. Carbon atoms are capable of forming multiple bonds with other carbon atoms. The compounds of carbon, which are linked by only single bonds between the carbon atoms, are called saturated compounds. For example, methane, ethane, etc. Compounds of carbon having double or triple bonds between their carbon atoms are called unsaturated compounds. For example, ethene and ethyne are unsaturated compounds. Based on the structure of the carbon chain, hydrocarbons are broadly divided into 2 groups: open-chain hydrocarbons and cyclic or closed-chain hydrocarbons. Open-chain hydrocarbons contain carbon-carbon straight chains. They are further classified into 2 types: saturated hydrocarbons and unsaturated hydrocarbons. Saturated hydrocarbons are straight-chain compounds containing only single covalent bonds. These saturated hydrocarbons are also known as alkanes. Methane and ethane are examples of alkanes. Unsaturated hydrocarbons are the straight-chain compounds containing double or triple covalent bonds. Hydrocarbons with a double bond between carbon atoms are known as alkenes. For example, ethene. Similarly, hydrocarbons with triple bonds between carbon atoms are known as alkynes. For example, ethyne. The compounds of carbon which contain a closed ring of carbon atoms are regarded as cyclic hydrocarbons. They are of two types, alicyclic and aromatic. Alicyclic hydrocarbons are a category of carbon compounds which are in the form of a carbon cycle and contain 3 or more carbon atoms, thereby behaving like open-chain saturated hydrocarbons. For example, cyclopropane, cyclobutane, etc. The cyclic compounds which contain a single and a double bond at alternate positions and exhibit special properties are known as aromatic compounds. For example, benzene. Carbon compounds are categorized into various groups based on their functional groups. Carbon combines with many other atoms like nitrogen, oxygen, sulfur, and halogens, in addition to hydrogen. These carbons, which are bonded to heteroatoms, exhibit characteristic properties. Such a carbon atom together with heteroatoms is referred as a functional group. These functional groups impart characteristic properties to the molecule. When carbon compounds with similar functional groups were arranged according to the ascending order of the molecular weights, the difference between any two consecutive members of the series were found to be the CH2 group, and such a series is identified as homologous series. Let's consider the family of alcohols. The functional group in alcohols is OH. Methanol with a molecular formula CH3OH. Ethanol with a molecular formula CH3CH2OH. And propanol with a molecular formula CH3CH2CH2OH. We observe that the difference between methanol and ethanol and the difference between ethanol and propanol is by a CH2 group. Let's now analyze the characteristics of a homologous series. A general formula is used to represent a homologous series. For example, alkanes can be represented by a general formula CnH2n+2. In any homologous series, the difference between two consecutive members is a CH2 group. For example, in the family of alcohols, the consecutive members differ from each other by a CH2 group. The members belonging to a homologous series are prepared by similar methods. For example, methanol and ethanol can be prepared by the hydrolysis of methyl chloride and ethyl chloride with aqueous potassium hydroxide. A gradation in physical properties is seen as the molecular mass increases in any homologous series. For example, methane, ethane, propane, and butane exist as gases. Alkanes from pentane to dodecane exist as liquids, and higher alkanes exist as solids. So, with an increase in the molecular mass, there is a gradation of physical properties.